Hello everyone, welcome to my video. In this video, I will be covering 2D curvilinear motion and the XY coordinate system. Although we kept saying S, A, and V are vectors, but so far we have not really dealt with any questions specifically with directions. In the previous rectilinear section, all components were moving on a straight line. The only direction mattered was either the motion was going along a straight line, positive direction, or against it. We have also been dealing with, and you should be familiar with it now, the time derivatives of S, A, and V. In this course, we're only going to deal with 2D or say plane motions. Looking at this example here, the particle moves from A to A prime, which is not a straight line. In order to properly describe all motions happening in a 2D plane, we have to adjust our notation a little bit. We will use R for displacement, A and V for acceleration and velocity. However, please note that they are vectors. On slides, they are in bolded fonts, and in questions, I will be putting a vector symbol on top of it. But why the letter R though? R comes from the name radius vector. So that's why R, the letter, is used for displacement, not D or something else. Because we commonly refer to the position vector, so the radius concept faded out over time. Looking at the example here, using R1 and R2 to represent the position of A and A prime measuring from the origin O, we can calculate the total displacement from A to A prime as a vector -2, 2. The magnitude, or delta S, is given as square root of 8. Here, I want to show you that the displacement vector delta R is not affected by the selection of reference frame. Compared to the previous slide, I chose a different origin O, which changed the position vector. However, the displacement vector is still -2, 2. And this is a variable we are interested in, so which is not affected by the choice of different origins. From one point to the other, regardless of the path, we can always get the displacement delta R. This means we can calculate the average velocity by dividing the time it takes to travel between 2 points. Here you will see how R and S are connected. Since we have been using S for a while now before this class, let's be super clear about this now. S is the magnitude of vector R, or S is the magnitude of displacement, and R is a vector representing the displacement. Next, we'll go a step further by making the delta t infinitely small. This will give us the instantaneous velocity of the particle right at the point of interest. This is the same concept as we have been using for the past few sections when we were talking about the speed. So in curvilinear motion, velocity is always tangent to the path in the direction of motion. For example, looking at the V and V prime here, they are tangent lines at A and A prime. Graphically, we can connect the tail of the two velocity vectors. This will give us the delta V, change in velocity. Similar to what we did for velocity, here we can get either the average acceleration between 2 points or the instantaneous acceleration at the point of time of interest by making the t variable on the denominator infinitely small. Either we want to examine a rectilinear or curvilinear motion, we need a reference system. This is when the reference plane is coming in, so that we can report those variables of interest and be consistent once the reference system is set up and fixed in place. With the rectangular coordinates, aka the Cartesian coordinate system, we have the x and y axis. Along each axis, there is a unit vector. Why we need the unit vector, and to be honest, what is a unit vector then? From time to time, I see students get confused, so let me spend 1 minute here to explain unit vector. Let's say we have a segment length of 5 centimeters. Without defining the direction of the segment, this segment can be anywhere, right? Infinitely, they have infinite places to be on the plane. We also know from the algebra perspective or any similar advanced math courses in the past, that if we multiply a scalar and a vector together, we will get a vector. Keep these in mind, we can introduce the unit vector, which has a length of 1 and a parallel to the associated axis. For example, I is a unit vector of x-axis or x direction, and j is a unit vector of y-axis or y direction. We can now multiply this 5 centimeter segment with a unit vector I, and we'll get a 5i, which is now a vector with the length of 5 units or 5 centimeters and a clear direction. It's no longer at random place. It has a clear direction pointing to the positive x direction. For xy coordinates, we have 2 unit vectors, as I mentioned, I and j for x and y direction. But why we want this? Well, except for making things more complicated, sometimes working with vectors are actually easier, believe it or not, because the direction is automatically embedded in the vector. Unlike scalar, you have to read its direction every time and be careful with consistency. Also, with vectors, we can do operations like cross product, which we will use extensively later on when we are dealing with moments. You probably recall this concept from statics now. Therefore, all of the variables we know can be expressed in vector form as shown here, either for displacement, for velocity, or for acceleration. Those scalar equations we learned can still be used here, but just remind yourself constantly about what types of variables you're using. Are you dealing with vectors? Are you dealing with scalars? Just be careful. In the last 2 slides, I want to go over the projectile motion. Projectile motion is a unique one within the big curvilinear motion family. It is moving in curves. Why projectile motion is unique is because it can be broken into x and y direction to analyze each direction separately and then put that together, right? So as if you're analyzing 2 motions in one motion. You know what I mean. In x direction, we have the vx and ax, and in y direction, we have vy and the ay. They all have unique properties that can help us in solving problems. In an ideal projectile motion, there are some assumptions we often make. We ignore aerodynamic drag, we ignore the curvature of the Earth, we ignore rotation of the Earth, and we assume there is a constant acceleration, where in the x direction, there's no acceleration, and in the y direction, the only acceleration the object is experiencing is the gravity. So if we define y positive is going up, then ay is constantly negative g, or negative 9.81 meter per second squared in SI unit. Given the assumptions and proper launch conditions, which you would be given in question, the launch speed v0, the launch angle theta, and launch coordinates x0, y0, given these, the equations we developed already in rectilinear motion can be used here. Therefore, when you are working on a projectile motion questions, you are essentially analyzing 2 rectilinear motions. Here's a list of recommended readings for this section, and thank you for watching. I will see you next time.